Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. Exothermic and endothermic reactions. During chemical reactions, temperature may increase or decrease. In exothermic reactions, energy is released to the surroundings. The temperature of the surroundings increase. Examples of exothermic reactions are combustion, many oxidation reactions, and neutralization. During endothermic reactions, energy is taken in from the surroundings. The temperature of the surroundings decrease. Examples of endothermic reactions are thermal decompositions and photosynthesis. Investigating temperature changes, required practical. In method 1, reacting two solutions together, for example an acid and an alkali. The equipment used is a polystyrene cup inside a glass beaker. Inside the glass beaker makes it more stable. Use a polystyrene cup as it's well insulated and prevents heat loss to the surroundings. Add a lid, again to prevent heat loss to the surroundings. Use a thermometer to measure initial temperature and final temperature. A stirrer to continually mix the reaction mixture. Measure an appropriate volume of each liquid, for example 25 milliliters. Place one of the liquids in the polystyrene cup. Record the temperature of the solution. Add the second solution and record the highest or lowest temperature obtained. Change the independent variable and repeat the experiment. This independent variable change may be a different acid or different concentration of acid. In method 2, you're investigating temperature change, but when reacting a solid with a solution, for example a metal and an acid. Again, place the polystyrene cup inside the glass beaker to make it more stable. Measure an appropriate volume of the solution, for example 25 milliliters. Measure an appropriate mass of the solid, for example 2 grams, or select a suitable sized piece of metal. Ensure that the mass or the size of the piece of metal being used is the same for each repetition. Place the solution in the polystyrene cup and record the temperature of the solution. Add the solid and record the highest or lowest temperature obtained. Change your independent variable and repeat the experiment. Your independent variable could be the surface area of the solid, or the type of acid being used, or the type of metal being used. Reaction profiles. Reaction profiles are graphs that show the reaction progress, or time, from your reactants to forming your products on the x-axis, and energy on the y-axis. In some chemical reactions, the energy of the reactants may be higher or lower than that of the energy of the products. In exothermic reactions, the energy of the reactants is higher than the energy of the products. In endothermic reactions, the energy of the reactants is lower than the energy of the products. The overall energy change in an exothermic reaction will have decreased, whereas the overall energy change for an endothermic reaction increases and is noted as the energy absorbed. The activation energy is the minimum amount of energy required to start a chemical reaction and is labelled as the distance between the reactant energy and the maximum point on your curve. Typically, endothermic reactions have a much higher activation energy than exothermic reactions. This means that more energy is required to put into starting your endothermic reaction. This could be in the form of having to heat up your reactants or stir them, providing kinetic energy. calculating energy change of reactions. Overall bond energy can be calculated by calculating the energy required to break the bonds of the reactants, subtract the energy released when the bonds are made. You will be provided with bond energy data. For example, the carbon-hydrogen single bond requires 413 kilojoules per mole of bond to break. It also releases 413 kilojoules per mole of energy when a carbon-hydrogen single bond is formed. To calculate the overall energy change for the complete combustion of methane, we find the sum of the energy required to break the bonds of the reactants. That's 4 lots of carbon-hydrogen single bonds plus 2 lots of oxygen-oxygen double bond, giving us a total of energy required as 2,648 kilojoules per mole. Now we calculate the total energy released when the bonds are made. We have 2 lots of carbon-oxygen double bonds forming and 4 lots of oxygen-hydrogen bonds forming. We see this from the balanced equation, giving us a total energy released of 3,466 kilojoules per mole. By subtracting these values, we find the overall bond energy of minus 818 kilojoules per mole. Exothermic reactions give us a negative overall bond energy. This is because more energy is released when bonds are made versus a lower amount of energy required to break the bonds. As bonds breaking requires energy, energy has to be absorbed from the surroundings, making bond breaking an endothermic process. And as bond making is the opposite process, that must mean it is exothermic. Therefore, the calculated value for making bonds being greater than the energy required for bonds breaking means the overall reaction will be exothermic, giving a negative overall energy change. Chemical cells and fuel cells. The difference between a chemical and a fuel cell is this. Chemical cells contain chemicals which react together to release energy in the form of electricity. Fuel cells are supplied by an external source of fuel, for example, hydrogen. A battery is an example of a chemical cell. The voltage produced by a cell is dependent upon a number of factors: the type of electrode and type of electrolyte, electrolyte being the chemicals inside the cell. A simple cell can be made by connecting 2 different metals in contact with an electrolyte. Batteries consist of 2 or more cells connected together in series to provide a greater voltage. In non-rechargeable cells and batteries, the chemical reactions stop when one of the reactants has been used up. Alkaline batteries are non-rechargeable. Rechargeable cells and batteries can be recharged because the chemical reactions are reversed when an external electrical current is supplied. An example of a non-rechargeable cell would be a typical AA battery. An example of a rechargeable cell may be an electric toothbrush. Fuel cells are supplied by an external source of fuel. The fuel is oxidized electrochemically within the fuel cell to produce a potential difference. The overall reaction in a hydrogen fuel cell involves the oxidation of hydrogen to produce water. This is an advantage in industry as no pollution is occurred when water is the product of a chemical reaction. Hydrogen fuel cells offer a potential alternative to rechargeable cells and batteries. In a hydrogen fuel cell, the fuel enters in one side of the cell. The hydrogen loses electrons which provide the electrical current. the hydrogen losing the electrons provides electrons to the anode. These electrons are carried to the cathode by electrical wires. The electrolyte of hydrogen ions is in the centre of the fuel cell. The other reactant, oxygen, enters from the opposite side of the fuel cell. Oxygen and hydrogen can diffuse through to the electrodes and react together to produce water. Any unused gases or water leaves the fuel cell. At the negative electrode, hydrogen reacts with hydroxide ions, forming water and 4 electrons. At the positive electrode, oxygen reacts with water and gains 4 electrons to produce the hydroxide ions. Combining these two half equations, we ultimately end up with the overall equation of 2 hydrogen plus oxygen forms 2 molecules of water.